In the last video, we arrived at the normalized form of the probability density function, and we arrived at this form, and in the only challenge now was the determination of this value of alpha. So how do we determine the value of alpha? This is going to be how we start this video. Before we know the value of alpha, we should remember something from a 12th physics, something called as the equipartition principle, law of equipartition of energy. Now we will not be going into much detail, but the equipartition principle states that the energy of a molecule of an ideal monoatomic gas molecule. We have already written molecules, so energy of a molecule of an ideal monoatomic gas per degree of freedom is equal to half kBT. Now, firstly, what is the meaning of a degree of freedom? See, for a molecule, let's say for a molecule which is in say 2D, or let's not talk about 2D, let's talk about 3D. A molecule in 3D will have 3 degrees of freedom. What I mean by that is it can move in the z direction, it can move in the x direction, it can move in the y direction. So number of degrees of freedom is equal to 3. And it's better if we not say energy, but particularly use the word kinetic energy. Eventually we will realize that both the kinetic energy and potential energy of an ideal gas is 0, but for specifying, for making ourselves clear, we will only use that word kinetic energy. Use kinetic energy for now. So number of degree of freedom of the for the 3-dimensional case was 3, as there were 3 independent axes from which the gas molecule can move. Similarly, for the 2D case, for the 2D molecule, the number of degrees of freedom was equal to 2. Now this kinetic energy in the 3D case would be 3 into half kBT, because this was a kinetic energy per degree of freedom. Number of degrees of freedom was 3. We multiply it by 3 now, and we get the total kinetic energy of the system as 3 by 2 kBT. And the number of degrees of freedom for the 2D case was now 2 into half kBT, which is nothing but kBT. Now this is what our idea, this is what we should know about the equipartition principle. In the beginning of the derivation, we stated that our ideal gas was a perfectly monoatomic gas, and we stated it with the fact that we were considering the gas particles to be completely point masses and spherical, which can be approximated as spherical point masses, and a monoatomic gas is exactly that. So we should we have an idea of our equipartition of principle, and we should proceed forward. Now we have arrived at this form of the distribution function, so we will have to take this down again and again, and we should realize that this is actually a distribution of velocities, distribution of speeds in 2D. This is a 2D Maxwellian case, so this is a distribution of speeds in 2D, and to find out some average of some quantity, let's say we are finding the average kinetic energy, what we have to do is we have to let's say we have to find the kinetic energy. This is, let's say, the kinetic energy of one molecule was K. Okay, and we have to multiply it with dn. This dn was nothing but the total number of molecules. This is the number of molecules having the kinetic energy K, right? And then we will have to sum this up over an interval over all space, or the interval which is called which we call all space, from, let's say, c equal to 0 to c equal to infinity, and we have to divide this by total number of molecules. That is integration of dn c equal to 0 to c equal to infinity. This should be an idea of the average kinetic energy of of all the molecules of the system. Now, from our basic knowledge, we know that the kinetic energy is half m c1 squared, right? The average kinetic energy of each molecule of the gas of one molecule, not in is actually half c1 squared. And we know that this half c1 squared, well, okay, this is not the average kinetic energy. This is the kinetic energy of each molecule. So we have to average this kinetic energy using the formula given above, using the equation given above, right? So we have average kinetic energy, which can be written as c equal to 0. Rather, we have used c1, so let's replace it by c1. So we have c1 equal to 0 to c1 equal to infinity, and we have k. What should be the k here? So we will take half m outside, since mass of each gas molecule was constant, and we have c1 squared dn. So we write dn here, we'll write dn here, and dn will be put from dn was put from here. Yeah, so dn was, so what is dn? Not dn c1, we have used dn c1 before, so we will have so we will have the function as, okay, let's write it down here. Dn by n is actually 2 pi c1 alpha by pi e to the power minus alpha c1 square dc1. This was our dn by n. So we can take this n over here. We will take dn. Let's cancel the pi's. To 2 alpha c1 n e to the power minus alpha c1 squared dc1. So we have 2 alpha c1 n e to the power minus alpha c1 squared 2 alpha c1 n alpha c1 dc1. And this is and since our dn was a normalized function, so the integration of dn will be actually integration of basically this term was actually equal to n. So this is a normalized function, so we will divide this entire thing by n, wherein this n and this n will cancel out, and we can take the constants out to find an average kinetic energy, to find the average kinetic energy, wherein the 2 alpha will become a constant and come out of the equation, and half into m into 2 alpha, and there will be a c square c1 square c. So this is cq c1 cubed. since this is already in C1, so we will have 0 to infinity C1 cubed e to the power minus alpha C1 squared dC1, and we will have cancelled, we will have them cancelled, and we will have m alpha 0 to infinity C1 squared e to the power minus C1 squared dC1. So this is an integral that needs to be determined. Let's call this integral I. And now, so that our main focus is always on determining this integral I. How do we determine this integral? One way is to transform this into one way would be to solve this standard way. The standard way would be, well, we can write this is a C1 cubed, so this can be written as C1 squared into C e to the power minus alpha C1 squared dC1, and we will multiply divide by alpha. So we have this alpha C1 squared here, so alpha C1 squared, let's take it as T. Okay, so we have 2 alpha C1 dC1 equal to dt. 2 alpha C1 by dC1 equal to dt. So we have C1 dC1 is dt by 2 alpha. C1 dC1 was actually equal to C1 dC1 was dt by 2 alpha. So we will have 1 by alpha t 0 to infinity e to the power minus t dt by 2 alpha. So this should be the thing that we get. But the problem here is this integration can be done by a simple integration by parts, but there would be a problem. If you find, we will see that the first term would be t e to the power minus t, and if you put the limits in infinity, if you put the limits 0 to infinity here, the first term would be such that this would be infinity, this would go towards infinity, this t would go towards infinity, this would go towards 0, and there would be a problem, as 0 into infinity cannot be determined by we cannot write down 0 into infinity directly, right? So this is a problem right here. So, and eventually we will realize that this will be 0 into infinity will equal to 0, but there is no direct way to write it. So the way to proceed forward here was actually the use of something called gamma functions. Now this function can be broken down into gamma functions, and we will realize that this 1 by 2 alpha square 0 to infinity, this is actually t 2 minus 1 e to the power minus t dt. What is the reason for this 2 minus 1 is that this 1 by 2 alpha squared, this is actually the gamma definition of gamma function. So what is the gamma of n is actually defined as integral 0 to infinity t to the power n minus 1 e to the power minus t dt, right? So this is actually for nothing but this is actually, if you compare, this n is here 2 and this is gamma 2, and gamma 2 is actually this gamma function. There is a very special way of writing the gamma function here, is that this gamma of n can be written as n minus 1 factorial. So this is actually 1 by 2 alpha squared is actually 1 into gamma of 2 is just 1 factorial, and so yeah, okay, let's not put implies right now, we put implies here. We will have to change all the signs, which will for implies to equal to, as this is actually 1 by 2 alpha squared. So I came out to be 1 by 2 alpha squared. that is great. And if we have the average kinetic energy, the average kinetic energy, if I remember right, was half 2 mi, right? If I remember right, no, it was m into alpha, right here, m into alpha I. So we have m alpha I, and we have m into alpha into 2 alpha squared. We will have m by 2 alpha. Now this was actually the value of the kinetic energy, average kinetic energy of all the molecules in the system, on the perfectly ideal gaseous system. But we found out from equipartition principle, that's why I stated the equipartition principle before, that this was actually equal to, for the 2D system, since this is a 2D Maxwellian, this was actually equal to kBt. And thus we see that we have a value of alpha in terms of the value of the, on terms of the variables of the system, in terms of the state variables of the system. We have a temperature term here, so we can find out the value of alpha in terms of temperature, where then alpha turns out to be m by 2 kBt. So this is actually great news for us, and we will have to put it in our original equation. So our original equation would then turn out to be dN by n equal to, and we can actually copy our equation from here, and we will here we will copy and we will paste here. And delete the n out here. So we will have, yeah, so we will have alpha, the value of alpha being put over here, kBt e to the power minus alpha here. So alpha was also here, so this is m c1 square by kBt dc1 and we can cancel the 2 here. Yeah, there is a c1 missing here, so this is this c1, okay, this c1 came here, so I had missed that out, rubbed that out probably. This is 2 cancel out. This is mc1 kBt e to the power minus mc1 square by 2 kBt dc1. Okay, so this is our, so now we have the complete form of the 2D Maxwellian speed distribution or the velocity distribution of the 2D Maxwellian. The speed distribution of the 2D Maxwellian is complete, and this 2D Maxwellian gave us an idea, has given us an idea how to proceed about in case of the more important 3D Maxwellian, the Maxwellian 3D, the 3-dimensional Maxwellian. We will proceed exactly the same way as we proceeded in case of 2D Maxwellian. And how will we proceed is, we will state that the 3 directions for the 3D Maxwellian case are independent of it. 3 directions are independent of each other. That is, the probabilities, that is dn vx by n into dn vy by n into dn vz by n are multiplied to give the probability that the molecule was moving with a velocity, let's say c, with the speed c by n, and this c was actually vx squared plus vy squared plus vz squared, the root taken with the square root. And then we also state the same thing as we did for the 2D Maxwellian, was that the three directions had become were independent of each other, but not very different from each other. The isotropicity assumption. The isotropicity assumption enabled us to write that the same functional form for all the three directions. So this is f minus v, so vx. So we are just writing the 1D distributions for all the three directions independently. So this is a vx squared into a vy squared into a vz squared dvx into dvy into dvz, and this is a cubed, and since all the forms were like this, we will write directly that e to the power minus alpha vx squared into e to the power minus alpha vy squared into e to the power minus alpha vz squared. The simple isotropicity condition dvx, dvy, dvz. So this is a cubed e to the power minus alpha vx squared plus vy squared plus vz squared into dvx times dvy times dvz, and again we have a cubed e to the power minus alpha c1, not c1, we right now stated that this velocity was c squared dvx dvy dvz. Okay, and we again continue to state that this dvx times dvy times dvz was actually, in contrast to the previous case, this was actually the volume element. Last time we had an area element, now this is actually the volume element. And again we need to go back to the coordinate system, and what we would do is we will write this dvx times dvy times dvz into some form of this c. Dvx, dvy, dvz will be written in some infinitesimal form of the speed c, right? So that we can integrate this function easily to find out for our applications, which we will do later. Okay, so let's consider the 3D coordinate system. So let's have our z axis. This is our z axis. This is our y axis, and this is our x axis. We have a vector here, velocity vector here, which was such that it is from vx to vx plus, this is vx to vx plus dvx, this is from vy to dvy, vy plus dvy, and there is vz to vz plus dvz. It's difficult to draw in 3D, but you will realize that these three coordinates will actually form something like a cube here, and there will be, if you think about it, there will be a cube which will be formed here. In the last case it was a square, but in this case there will be a cube which will be formed, which will be something like this. I will draw it separately, that this cube will be this is not a cube but a cuboid, which will have dimensions dvx times dvy times dvz. This cube having dimensions dvx, dvy and dvz, and this cube was actually the required range of all the velocities which were in the range range of all the velocity vectors which were in the range vx plus dvx, vy plus vdy, dvy plus vz plus dvz. And we will translate this entire thing. We can translate this entire thing into some c to c plus dc. And we again go back to our what should be the point density here. The point density was nothing but this number of molecules in a small number of molecules which lie in this range of c to d, c plus dc, divided by the volume element, which will be the dvx times dvy times dvz. For now we will treat these infinitesimal terms as simple decimals, simple fractions. Now this dn or this let's say this dnc for now is actually this point density into dvx, dvy, dvz. We can compare with this equation, right? Then compare with their equation, and this is actually a density, which is actually the point density here in this case. The point density was a cubed e to the power minus alpha c squared. A cubed e to the power minus alpha c squared into dvx, dvy, dvz. Now again we will argue that this is not actually this is actually for one velocity vector, one velocity vector which is somewhat like this, which is somewhat like this. We shall draw it again to make it easier. We will have to draw it again, which is somewhat like this. There is one velocity vector with the velocity cube here, right? But since we are talking about speeds now, there will be, this is actually an 8 octant. There will be 8 such octants in this coordinate system, and for this coordinate system, since we are talking about a speed, there will be infinite speeds in all the directions with the same magnitude or the same distance from the origin. Since it will be equidistant from the origin, and if we talk about the locus of a point in 3D, which is equidistant from a certain point or the origin, the locus will actually trace a sphere. Okay, it will trace a sphere, and since it's difficult to draw a sphere in 2D, we'll try to draw a projection of to make the thing simpler. So there is a sphere. This is a sphere, and if there are cubes lined up, infinite such cubes lined up, these cubes will actually form a outer concentric sphere, and this concentric sphere will actually result in the shape of the volume wherein all our velocity vectors will lie. All our velocity vectors will lie between this ring like shape, right? This ring like shape will have all our velocity vectors, all the velocity vectors that we need, and this volume of this shell, this infinitesimal shell, will be given by dv shell. This dv shell will actually be given by, since they are, remember that this is actually at a distance c, and this is actually at a distance c plus dc. We have translated the problem from velocity to speed, so the volume will be given by 4 by 3 pi c plus dc whole cubed minus 4 by 3 pi c cubed. And with the same logic as we applied, this should be 4 by 3 pi c cubed plus 4 by 3 pi dc cubed, or since this is a c, or we should do it this way, that this is 4 by 3 pi, we have c plus dc whole cubed minus c cubed. So we will have 4 by 3 pi. We are finding the volume of the shell, so this should be the volume, so this should be c cubed plus 3c squared dc cubed dc plus 3c dc cubed dc squared, sorry, and dc cubed minus c cubed. So this c cubed will cancel out, and these are all the higher order infinitesimal terms with the power more than 1, that is, they can be taken as 0. Since they are already infinitesimal, cubing them would make them even more closer to 0, negligible. So this 3 and this 3 cancel out, and the answer is 4 pi c squared dc. So this is actually the volume of the shell, right? And the number of molecules, total number of molecules in the speed range c2 c plus dc, which is given by d and c, will be equal to now the point density. Point density is uniform for raw gas molecules into this dv shell. Now this point density was actually a cubed e to the power minus alpha c squared, and this dv shell was 4 pi c squared dc. Perfect. So we have our equation, and this is the c squared, this is the equation that we have right now. So the next task which is at hand is actually the determination of a and alpha. We are proceeding in exactly the same way as before. Determination of a and alpha, and we will determine a by simply normalizing the wave function, normalizing the probability density function, which we shall do in our next video.